Let us begin. Today we are going to discuss quantum many-body systems. And the first one, maybe the simplest one and the most illustrative, is the quantum rational Calogero-Moser system. We discussed it at classical level, and we obtained it by considering reduction from Knižnik-Zamolodchikov equations. And today we are going just to discuss how to solve the corresponding Schrödinger equation. Let us write down the Hamiltonian. This is the Laplacian, quantum kinetic energy, then the interacting term. The interaction is like this. Yes, it's inverse squared potential. And we also add harmonic potential. Like this. And this G is equal to nu times nu minus h. As you maybe remember, last time we discussed it, that the classical coupling constant requires some quantum correction, which is given here, and we had it last time when we obtained the Calogero system from reduction from Knižnik-Zamolodchikov equations. Okay, now so what are we going to do? Let us first consider the simplest case, n equals 1. Then we don't have any interaction with Calogero potential. We have just the Hamiltonian for harmonic oscillator. Let me put it on the squared q squared and a half. And so it means that we have a very simple model, but let me recall you how it can be solved, and the way how we solve it will be used then for generic Hamiltonian. So there are a lot of ways, of course, how to solve harmonic oscillator, but the way I'm going to show you is the one which is extended to this Hamiltonian. So let us do it. We introduce two operators, the creation operator and the annihilation operator. This is a creation. And this is annihilation. A simple statement is that this Hamiltonian is rewritten in terms of these operators And it is represented in the form creation, then annihilation, plus some E0, where E0 is a energy of ground state. This is the energy of ground state. And the ground state itself is given by the following function. It is just an exponent, the Gaussian exponent. This is the ground state. And it has the following properties. It vanishes under the action of annihilation operator. And if you act by creation operator, then you generate some excited states. So what is the way how to solve the model? The way, let us consider a conjugated operator, H prime. And H prime is defined as conjugation of H minus energy of ground state. And the conjugation is by the wave function of ground state. So what is written here is just like this, and this is we mean that it is just a composition. Yes, so the differential operators act not only on the ground state, but they act on something which stays here. So it's a operator composition. Then it's a simple exercise to show and to verify that this is just the following expression. This is H prime. And now we're going to look for polynomial solution of eigenvalue problem for this H prime. In fact, there are a lot of different solutions. I mean, different classes of solutions to this Calogero-Hamiltonian. Some of them are given by some complicated integral representations. But what we are discussing today is a class of solutions given by symmetric polynomials. It is quite simple to define, quite simple to look for some explicit formulae, and this is why we begin with it. So we are looking for a solution here. If we talk about this oscillator, we are looking for solutions in some basis of polynomials of some fixed degree n, for example. So we fix n, and then this is like our basis. You may denote it like E0, E1, and so on, En. And let us write just some solution. So we're going to make a substitution and look for if it works. So we fix some highest power, let it be n, and consider some arbitrary polynomial of variable q. So that it begins with C0, multiplied by Qn plus C1 Qn minus 1, and so on up to Cn. And we assume that C0 is not equal to 0. Yes, because we fixed this power n. Okay, let us act by this H prime and look what we have. So the action of H prime on this phi n is equal to, let us write it accurately, minus H bar squared 1/2, and the sum goes from k equals 0 to n minus 2, because this operator reduces the power by 2, and we have here ck multiplied by n minus k, yes, and n minus k minus 1. This is a result of double differentiation, and here we have n minus k minus 2. And this operator saves the degree of polynomial, because at one time it differentiates and then multiplies by q again. So we have, here we have plus h omega, and the sum from 1 to n, ck n minus k, q to the power of n minus k. And this should be equal to En times phi n. You may consider, of course, it in the general case from the very beginning, but maybe it is a little more easy to look at some example. For example, let us consider the case when this n small is equal to. Special case when degree of polynomial is 2, it is just quadratic polynomial, c0 q squared plus c1 q plus c2. What we have? The action of h prime on this phi 2 is equal to, let us look at it. Yes, when we act by Laplacian, we have only this term, and it is minus h squared c0. And when we act by this operator, then it gives us 2 more terms from this and this one. So here we have 2c0 h omega q squared plus c1 h bar omega q. And this should be equal to E2 prime. I will denote E2 prime. So this should be also prime, because we are looking for eigenvalues now of h prime. E2 prime multiplied by c0 q squared, c1 q plus c2. And we have just 3 equations for coefficients, which appears by considering all possible powers of q. And these equations are as follows. For this power q squared, we have from the right we have c0 E2 prime, and from the left we have this expression, yes, 2c0 h omega. And since c0 is not equal to 0, then it means that E2 prime should be equal to 2 H omega. The next order is Q, and here we have C1 multiplied by E2 prime is equal to H omega C1. And as you can see, if C1 is not 0, then we obtain incorrect answer, because E2 prime here is equal to 2 H omega, and if we cancel out C1, then we obtain a different answer. So this means that C1 should be equal 0. And finally, free term, Q in the power of 0 provides minus H squared C0 is equal to C2 E2 prime. And we know this E2 prime, it is equal to 2H omega, so that the later gives us C2 is equal to minus H divided by 2 omega C0. So this is a kind of answer, and then we may also perform some normalization. But let me just, this is a simple illustration, and if we consider a general case, I mean this substitution, then we find the following result. The result is as follows. All Ck is equal 0 for all what K. So this is what we saw here, that C1 is equal to 0. And in the general case, Ck is equal to 0 for all odd K. And for all even K, we have a recurrent relation. Yes, and I should say from the very beginning that Ek prime is equal to En prime is equal to N H omega. And for even K, we have the relation between Ck and Ck minus 2. It is minus H divided by 2 omega and minus K plus 1 and minus K plus 2 divided by K and multiplied by Ck minus 2. This is a recurrent relation, and so in order to have just properly normalized solutions, we finally choose C0 to be a certain constant. Let me write it explicitly. It is like this, and then Ck is equal to minus H over omega in the power of K half, K1 half, then N factorial divided by N minus K factorial. And we also have here C0 divided by this expression. So this is the final answer. And this provides, if we just substitute all these coefficients into this into initial definition. Yes? No, maybe I should put like this. Yes, C0 is not substituted. But this C0 is needed. That, let me say in 1 minute. Just these coefficients provide us an answer given as Hn of omega divided by h of q, and these are Hermite polynomials. These are Hermite polynomials. With this coefficient, this provides solutions which form orthogonal basis and properly normalized basis functions. But you should remember that this is a solution of this problem. These are eigenfunctions for h prime. And we were looking for the functions initially for h, and this h was related with h prime as given here, so that the final answer is for eigenvalues of h is given as En prime plus E0, and this is just n plus 1/2, which omega is well known. And the psi n, the eigen functions of the original Hamiltonian, is given by this ground state multiplied by these Hermite polynomials. And these solutions are properly normalized, and this is the way how we fixed, in fact, this C0. Okay, so now we considered, just briefly reviewed, main idea of how to construct solutions for harmonic oscillator. And in fact, what we are going to do is very similar thing. But now we will do it for this Hamiltonian H. So first statement is the following. Now we are looking at this Hamiltonian, and our statement is as follows. This H is represented in the following form. The sum from 1 to n. Here we put operators which are similar to creation and annihilation, plus E0, where this E0, the energy of the ground state, is equal to 1/2 n omega multiplied by h, and plus n minus 1 mu. This is the ground state energy, and these operators are as follows. This is analog of annihilation and creation operators. H differentiation with respect to qi plus omega qi, and minus sum over j not equal to I from 1 to n, and here mu qi minus qj. And here we have the same thing, but this differential operator with the opposite sign. this can be verified straightforwardly. Maybe we can do it in some simple case. For example, let us put n equal 2, and let us consider A1 and A1. What we have then? So let us write it explicitly. Then it's minus h d1 plus omega q1 minus nu q1 minus q2. Yes, this is this operator, and then it is multiplied by the same but with opposite sign. Behind derivative. And so let us simplify this expression. Then what we have? So you see, first let us consider the action of this differential operator on what we have here, on the second bracket. Then we have minus h squared d1 squared. And then it acts on this. First it differentiated. Then we have minus h omega. Then this acts on this, yes. And then this acts on this. We have minus h nu q1 minus q2 squared. And we should also add the term which corresponds to when this derivative acts on some function standing to the right. So we should also put omega q1 minus nu q1 minus q2 minus h d1. So then this operator acts on some function standing here, and we just multiply by this coefficient. And we also finally have this function multiplied by all these brackets. So we also have plus omega q1 minus nu q1 minus q2 multiplied by h d1, and plus omega q1 minus nu q1 minus q2 squared. So this is the answer, yes. And we may slightly simplify it. What we see that these brackets are cancelled out. And what we have here is minus h squared d1 squared. We also have plus omega squared q1 squared. And we also have, you see, when we compute the square of this term and add it to this one, then we obtain nu squared minus nu h, q1 minus q2 squared. And the last one term is the mixed one. When we have here the 2 nu omega q1 minus q2. This is the result for this expression. And if we compute A2 for A2 plus A2. Then the result is, of course, the same, but we should just interchange indices 1 and 2. Then we get minus h squared d2 squared plus omega squared q2 squared plus nu squared minus nu h divided by q2 minus q1 squared, and minus 2 nu omega q2 divided by q2 minus q1. You see? So if we now, yes, and I forgot also this term. I'm sorry. I should also put it here, minus h omega and minus h omega. So and now we should sum up to these results, and also consider 1/2 of it, yes, as given here. Then we have the kinetic term from these two terms. We have also harmonic potential from these two terms. We have also Calogero potential from these two terms. These constants are going into eigenvalue, and these two terms, if you look attentively, when you sum up, then the dependence on q is cancelled out, and we have here just the constant 2 nu omega minus 2 nu omega, and this provides us this input into ground state. We should compensate it. Yes, we have minus h omega here and minus 2 nu omega from here. And we don't have these constants in the Hamiltonian. Therefore, we should put some additional constant which compensates that constants. And this is exactly this E0 which is written here. Okay, so we fix this statement. And we also need now, just following the same line as we used in harmonic potential, let us also define the ground state. This ground state delta of q will be given by the following expression. It is a product of the exponents which we used in the harmonic potential. They're just the same exponents. And this is multiplied by Vandermonde function in the power of beta, where beta is mu divided by h. And this is also called the Laughlin function. This is the Laughlin function, and one can verify some analog of what we had in the harmonic potential, that this operator AI is a kind of annihilation operator. It acts on the Laughlin function by 0. In fact, it's quite easy, because this is just a linear operator, and when you just act by this differentiation, you see that this provides you some some term coming from this exponent, and this is exactly is compensated with this one. And when you differentiate the van der Monde function in this power of beta, then you get exactly this sum, which is just compensate compensate the result of action of this differentiation on this term. Next, we should consider this conjugation, and let me write down the result of this conjugation. The result of this conjugation is H prime, and this is the following operator. Now we have the kinetic term plus the term which we had in the case of harmonic potential, but now it is sum up overall possible indices. And additionally we have minus h nu sum over I less than j 1 over qi minus qj and the difference of the first order differential operators. So we our conjugation provides the terms with which depends linearly on differential operators, but cancels out the potential. So instead of Calogero-Moser potential, now we have this term which is a first order differential operator. And so what we are going to do? We are going now to solve eigenvalue problem for this H prime operator. And we again denote it like some phi n. And we will look for this phi n in the class of symmetric polynomials. So for this purpose, so in general, let me introduce some notations. We have we'll denote q to the power of lambda the following expression: q1 in the power of lambda 1 and qn in the power of lambda n. So this is in fact called a partition, and lambda i's are parts of this partition. We assume that all these lambdas are non-negative integers, and let us also assume that lambda is greater than lambda 1 is greater than lambda 2, and so on. So we have some kind of ordering. And the length of partition, let me also introduce this notation. So in fact, we may have some powers can be equal to 0. So the length of the partition is a number of parts. So this k is a length length of partition, so number of parts. And it is also usually written as the so-called Young diagram. Young diagram. Which consists of some boxes, some number of boxes, and this is the largest one. It is lambda 1, then lambda 2, and so on up to lambda n. So this is a basis in monomial symmetric functions. So we may use, in fact, different symmetric functions, polynomial symmetric functions, but here we use this definition. So having some partition given by a certain Young diagram, we may write down this monomial, and we're going to look for solutions in this basis. But let us first consider some example. Some simple example. For example, when we have just qi in the power of lambda I and some qj in the power of lambda j. So what is the problem, in fact? The problem I'm going to discuss is the following. You see, if we are going to look for solutions in the space of certain polynomials. But here we have some expressions, some operators, which may not preserve the space of polynomials. For example, when we act to a certain monomial by this derivative, it maps a monomial to another monomial because it just differentiates and decreases power of corresponding q. This operator saves the degree of corresponding q, and so again maps a monomial to monomial. But this operator do not preserve monomial, because when it acts on this expression, it also multiplies it by this ratio. And if we have this ratio, then the result of application of these differential operators to this monomial multiplied by this ratio is not a monomial. So, and what to do? And the answer is as follows. It is true that the action of this operator on this expression is not a monomial. But if we consider symmetric polynomials, then the action of this operator will preserve this space. So what should we do? We should symmetrize this expression, and the statement is that the action of this operator preserves the space of monomials. And let us verify it, because this is maybe the most important part. Yes, it's a statement that this operator has solutions in the space of symmetric polynomials. And it means that the action of this operator should preserve the space of symmetric polynomials. And let us verify if it is true. Okay, let us consider the action. So we are looking for the action of this operator only. We are not looking for the action of the total operator, but just we are looking for the action of this operator. on this concrete monomial. So this is what we are going to compute. dqi minus dqj, and this acts on qi lambda I, qj lambda j, plus qi in the power of lambda j, qj in the power of lambda I. So let us write what we have. We have this 1 over qi minus qj, and the result of so we act first by this operator to the first term, and then we have lambda I q I lambda I minus 1 qj lambda j. This to this, yes. Then this to this minus lambda j, qi in the power of lambda I, qj in the power of lambda j minus 1. This is the action of this operator to the first term. Now we write the action of this operator to the second term. Then we have plus lambda j, qi lambda j minus 1, qj lambda I, and minus lambda I minus lambda I qi lambda j, qj lambda I minus 1. That's it. Let us now write it in the following way. We collect this term with this one because we have lambda I as a coefficient here, and we put it as follows. You see, we put lambda I and q, and we write it like qi in the power of lambda j and qj in the power of lambda j as well. And here, inside the brackets, we write like qi in the power of lambda I minus lambda j minus 1 minus qj in the power of lambda I minus lambda j minus 1. So you see, if you multiply this by this expression, then you have the power lambda I minus 1 as we have here. And when you multiply this to this factor, then this provides you the second term. Okay? And we also have the coefficient minus lambda j qi, and here so now we are looking for these terms, and we write them as follows. The common factor we write as lambda I in the power of lambda j minus 1, and the same for qj, also lambda j minus 1. And then in the brackets we have again similar expression, but with different psi of 1. So let me write it, and then I explain. Lambda I minus lambda j plus 1 minus qj lambda I minus lambda j plus 1. So if you these are expressions, this and this, and these are expressions, this, the first and the last. Why we did it? We did it by the following reason. We are now going to use a very simple statement that if you have some x to the power of n minus y to the power of n divided by x minus y, then it is just x and to the power of n minus 1 plus and so on.
Is it sufficient to check these effects only for the Newton polynomial or just elementary polynomial?
We'll look for solutions in terms of this elementary monomial polynomials which I wrote using the Young diagram. So in fact, you should, of course, verify it for an arbitrary monomial function, which is given by product of all q's in some powers of lambdas. But we just check in some simple case just to see how it works. And now it can be written, this result can be written in two ways. The first way is to write the sum from 1 to n like this. And the second way is to write just the same sum, is to put limits not from 1 to n, but from 0 to n minus 1, and to write like xn minus k minus 1 y to the power of k. So it's just the same, but we're also going to use it here. So we just divide these brackets by this expression, and so main result is already done. We see that this expression is in fact can be divided by this difference, and we get something. But let us write the result, what we get. The result is as follows. We have here, from the first bracket, we have some lambda I qi lambda j q j lambda j. So I am rewriting this this factor, and now we write down the ratio of this bracket by this difference in the form of the sum from 1 to n. So we put here the sum from 1 to lambda I minus lambda j minus 1 qi to the power of lambda I minus lambda j minus 1 minus k qj to the power of k minus 1. Here we applied this sum, and when we write down the second term, we use another sum with another limits. So we have here lambda j qi to the power of lambda j minus 1 qj to the power of lambda j minus 1. This is this factor, and now we write the ratio in the form where sum goes from 0 to n to n minus 1, and n here is this power. So we have here lambda I minus lambda j. And now here we have qi in the power of lambda I minus k minus 1 and qj no, I'm sorry, it's not true. Here we have the power is lambda I minus lambda j minus k. And here we have qj in the power of k. So this is a current result. Now we don't need any more middle of the blackboard. So let me continue. Let me continue. So now we just multiply this. We put these factors inside the sum, and then we have lambda I sum from k equals 1 to lambda I minus lambda j minus 1 in the power of qi. And in the sum we have qi in the power of lambda I minus 1 minus k. And qj is in the power of lambda j plus k minus 1. And minus lambda j multiplied by the sum from 0 to lambda I minus lambda j, and qi lambda I minus k minus 1, qj lambda j plus k minus 1. So we have just the same expressions on the sums. This is why we used two slightly different representations with some different limits. It was just exactly for this purpose. Just we have the same expressions on the sums. And the later means the following. We may unify, partly unify, yes, because this sum has two more terms with respect to this one. It has the term with k equals 0 and k equals to lambda I minus lambda j, while this sum doesn't have it. So, but at least we may unify and write it like lambda I minus lambda j multiplied by the sum from 1 to lambda I minus lambda j minus 1 with these expressions. And we also have two more terms coming from this sum for k equals 0 and for k equals lambda I minus lambda j. And this gives us minus lambda j multiplied by qi lambda I minus 1, qj multiplied by lambda j minus 1, and plus qi lambda j minus 1, and qj lambda I minus 1. So this was just a verification of how this operator acts on this expression. And we of course can easily compute how this part of the Hamiltonian acts on this expression. There is no problem at all. But so what we want to do? What is the next important result? In fact, we of course may. So what we obtained currently is that this operator acts on the space of some symmetric polynomials. And of course, you may choose different bases in symmetric polynomials. For example, so I think we don't need it anymore. There are several natural bases in the space of symmetric polynomials. For example, you may consider power sums. And these are just these type sums, yes, as the first possibility. Second possibility is to consider elementary symmetric functions, which are usually denoted by E. So this E, K, and they are given by sums of this form. And we can also consider what we begin with, the monomial symmetric functions. All of them can be expressed through each other. For example, there is a determinant formula which relates power sums with elementary symmetric functions, and it's given, so it's called determinant formula. So if you have this pk, you should write down matrix k by k, which is like this: E1, 2, E2, 3, E3, and so on, k, ek. Then the rest, the rest of columns are without these coefficients. Just you put E1, E2, and so on up to ek minus 1. Here you put E1 and so on up to ek minus 2, and so on. And finally, you have here E1, and you should also put one more diagonal with ones. And the rest is 0. So there is a relation of this type. For example, just let me just give you an example. When okay, let me write it here. When n is equal to, then what we have? We have this P1 is equal to Q1 plus Q2. P2 is equal Q1 squared plus Q2 squared. And what is E1 and E2? E1 is Q1 plus Q2, and E2 is Q1 times Q2. And what is written here, for example, is that P2 is E1, 1, 2, E2, E1. So you may verify that it's E1 squared minus 2 E2. And it's easy to see that if you put here the square of sum, Q1 plus Q2 squared minus 2 products of Q1 minus Q2, then you obtain, of course, this Q1 squared plus Q2 squared. So this is just a comment about about symmetric polynomials, I mean that you may use different bases. And what we use is the basis of monomial symmetric functions, which I previously wrote. Let us write it again. M lambda, these monomial symmetric functions. So they are defined just by sums over all possible permutations of q's in these powers defined by parts of some partition. And this is the action of this permutation group. So the sum is overall possible permutations.
We use these spaces?
Yes, we use this one. I just recall that there are very standard and widely used bases in symmetric polynomials, like power sums and elementary symmetric functions, but we use slightly different definition, which is this one.
Why is it bad in my view?
Maybe it is not bad, but the result is the result I'm going to formulate is valid for this basis, and it looks very nice. Let me say. So what is the main result of the statement? Statement or theorem. The statement is the following. Let us consider these monomial symmetric functions. Then the action of this h prime to m lambda is given by h omega modulo lambda. This modulo is a sum of all lambdas. This is I previously wrote definition plus some linear combinations of m mu with coefficients with some coefficients, and mu is less than lambda. It's a dominance partial order, so mu less than lambda. It's a dominance partial order, and it means that the partial sum of all parts is less than another partial sum, and this is valid for all j. So why it is important? So and this we're not going to prove it in the general settings, but you may find it in the literature. It's a known statement, but it requires some time to prove it explicitly. I think we just demonstrate some properties, but we're not going to prove all statements accurately. You may easily find it. And so why it is important? It is important by the following reason. You see that the action, so let us write it, the action of the action of H prime on the space on M lambda is given by triangular matrix. So if we write down all these functions which form bases in symmetric polynomials, then what we see. So suppose we somehow write all these m's numerated somehow. So what we see here is that the action of this operator provides some diagonal part and some triangular part, which fills the matrix in the following way. So we have this operator acts on the space of these monomial symmetric functions as a triangular matrix. The latter means that the diagonal elements of this matrix are eigenvalues. So we choose such a basis in the space of symmetric functions that the action of this H prime is given by triangular matrix. Therefore, these elements which are standing here on the diagonal are exactly the eigenvalues. Yes, because if you write down characteristic equation for triangular matrix, then the set of eigenvalues just coincides with the elements standing on the diagonal. And therefore, these are exactly eigenvalues of this Hamiltonian. This is why it is important. So we may write as a consequence of this statement, we may write that E lambda prime is equal to H omega lambda, or just by definition, it's just the sum of all lambdas from 1 to n. So we have a result for the eigenvalue. And finally, of course, we may come back because we had here some conjugation with this Laughlin function, and then we may come back to original Hamiltonian. And if we come back to original Hamiltonian, then E lambda is equal to E lambda prime plus E0. And let us just write it. Then it is H omega by the sum from 1 to n, and plus this expression, plus 1/2 nh omega plus n by n minus 1 mu omega divided by 2. So, and this is a spectrum of Calogero-Moser Hamiltonians. And so the ansatz. So now what we need is just to we found the spectrum, and we may, of course, we need to find some eigenvectors, and the statement that eigenvectors can be found using this ansatz. Ansatz, I mean, you may put m lambda plus some terms u mu lambda with m mu, where mu is less than lambda. If you write this ansatz for eigenvectors, then you will find out that it works And these are the so-called generalized Hermite polynomials. So this is just a kind of special symmetric polynomials, and you may just all these coefficients are fixed, and you may just find a list of it in some tables. And this is the answer. This is the answer in terms of symmetric. So you may construct solutions in terms of symmetric polynomials, and at least we found spectrum, and we just formulate. We didn't find it, but we formulate that it is possible to find solutions to eigenfunctions in this form, and these coefficients are explicitly determined. These are in fact orthogonal symmetric polynomials. I mean, there is some natural scalar product on the space of these polynomials, so everything is good. This is a good object, and just for some small numbers of lambda, you may explicitly write down all these coefficients. And this is, for example, is given in the book by Aratyunov. You may find some details in it. And I think this is all for today. And next time we will discuss also trigonometric Calogero-Moser model and Rosenars model. This will be on the next time.